So as Caitlin says, my name is Ian Ozsvald. Welcome to this talk on high-performance computing. And yes, I'll introduce myself. And it's my first time back in I think it's 4 years. I spoke 4 years ago on a related topic. So I'm very happy to be back, and I'd be very happy to hear any feedback from you, from those of you who were at my talk some years ago, and we can talk about the differences. So I'm an interim chief data scientist. What does that mean? It means I run my own consultancy, and witnessing the rampant job title inflation that has occurred in our domain over the last bunch of years, where with 2 years you become senior, head of everything. I was, well, how do I, as an independent consultant, compete with this? Well, obviously I can declare myself to be whatever I want to be, so I'll just be chief. So I get to be the chief data scientist and T-boy and the only data scientist in my company. I've been doing this for almost 20 years, so I also don't feel embarrassed to self-declare as a chief. I've been doing this from way back when it was AI, way before we had the term data science. And one of the things that I do is I quickly help teams build strategic data science plans, and then I help the teams act upon those and deliver things that actually work. So I'm very hands-on, I'm very practitioner-led. For me, it's all about doing the data science. I talk about it to demonstrate to myself that I know what I'm talking about, but really, for me, it's all about being hands-on and getting on with it. And I also run some public courses, and I'll mention those later on. So I work with a bunch of larger organizations, the kind of names that you might know, like Channel 4, ITV, QB Insurance, a multinational insurance company, and a whole bunch of small and mid-sized companies. And right now I'm working with one of the top-tier venture capital firms, helping them on their data science journey. And so the topic we'll cover here is based on both client and some of my coaching experiences in the last year. So this one's grounded in reality. I'm also co-author of the High Performance Python book published with Micha Gorelick with O'Reilly. We're just finishing off the manuscript for our second edition at the moment. I say just, I've got 5 weeks to go, I've got to get to Christmas, and the manuscript is going to be in. I'll be doing a book signing later on this afternoon on the first edition. We'll have 20 or so copies. You're very welcome to come and queue up and get one of those copies. And I'm very interested to hear your feedback about what it is you want to get out of high-performance Python. Before we proceed, I would like to get a photograph of all of you. Some of you may not wish to be photographed, in which case just duck or hide or whatever. The rest of you, I would love a happy, smiling photograph with a hand wave, please. And I know that when you've got a random speaker on stage saying, hey, make a physical action, you're probably not going to do it. I'm just going to pick on you until your hands go up. So we can do this nice and quickly. If you all, please, put your hands up and smile and wave. Because I'm assuming you actually want to be here, right? There we go. Perfect. Thank you very much, everyone. So that'll be on my blog entry later on. So today's goal, we're going to talk about making some Python code for data science go faster. This is based on some real client experience, particularly based around using Pandas and making that go faster. We're going to look at profiling to understand what's going slow and why. Look at various techniques to run the code to make it run quicker, and then look at ways to make it run in parallel and even to compile it, all with very minimal effort. And these are techniques that I actually use in my day-to-day client consulting. Also, when dealing with high performance, it's not just about going faster just because we can go faster. We have to be thinking about how we individually and as a team are acting performantly. And so I'll give you some reflections at the end, and this is one of the things that I've added to the book this time around, reflections on how to actually be highly performant in a real-world scenario. Now, we should make sure that I'm in the right room, first of all, so can you put your hands up, please, if you are Python developers? I just want to get a feel for you. Oh, brilliant, okay, right. Most of you fine. And how many of you use Pandas on a fairly consistent basis? All right, great. And keep your hands up if you still use NumPy directly on a consistent basis. Oh, great, right. You should all get lots out of this talk then. All going well. So here's a typical high-performance task. I've got a lot of data. I want to calculate a thing, and then we'll break this example out in a moment. And then it goes too slow, and I want it to go fast enough so that I can get my job done and move on to the next task. In this case, I want to analyze some time series data. I've got 100,000 rows of time series data. I'll show you on the next slide. And then we've got, so we've got 100,000 rows, we've got columns. The columns represent the time series per row, where the row is an individual person. And we'll make up a fake problem here. The fake problem is, I'm working with a mobile telecoms company. They've got 100,000 users worth of observational data. They know how many hours you're using your mobile phone every day, and they want to analyze this. They want to analyze it. Perhaps they're applying some promotions. They want to see if when a promotion is applied, some people use their phone more and some people use it less. And then maybe there's geographic constraints and other interesting things. We don't care about the data science component of this. We care about enabling the analysis to occur fast enough so that it gets out of our workflow. So here, I've got 14 columns worth of data, the number of hours you've used your phone every day over 2 weeks, and I want to calculate the slope of the line, so using it more over 2 weeks or less. And this becomes the basic problem we're going to look at. We'll do some timings and then we'll build this up. We can make this problem much harder. Rather than having just one 2-week window, we could have 2 years worth of 2-week windows. That's 52 weeks times 2, so that's 100 times more data to process. And rather than just having 100,000 rows, mobile telecoms companies have lots of users, so maybe you've got 1 million or 10 million customers to analyze. So it's very easy to make this kind of problem run 10 times or 1,000 times or 10,000 times slower, and then we have to make it go faster. So it's going to run slow. How do we make it go faster? So this is what the data looks like. Here's 5 rows just taken from the head of the data frame, 14 columns, just some integer counts of the number of hours that we have. And then we want to add column M, the rightmost column, that's the slope of the line, and then that graph on the right, that's row 3,400 or so from this data set, where it turns out that has the most increasing slope. So we've calculated M, and then we've searched for the most increasing, and that's the example there. And you can imagine most decreasing would look inverted the other way around. So let's look at 2 possible solutions. I'm going to propose that if asked, Ian, find the angle of the slope on a set of data, the first thing I would do, just being a diligent, sensible Python data scientist, would be to turn to scikit-learn and use the built-in linear regression model. It's there, it works, it's debugged, it's easy to use. There's a million examples. My colleagues will understand it. There'll be no surprises using this solution. So that's the topmost solution there, a couple of lines long. I pass in a row of data from the Pandas data frame. I pass in that row, I make a linear regressor. I pass in my inputs, which is 14 days, so 0 through 13 as a single column. I pass in the row of data, that's the number of hours used per day, that's the Y. I fit it, and then from that fit, I pull out the first coefficient, and then that's the slope of the line. And that's it, job done. Because I'm diligent, I've done a bit of Googling, I've thought about, hey, maybe there's other ways of solving this problem. I realized that in the numpy package, there's a linear algebra subpackage, and that contains a least square function. This, according to the manual page, says that it will do the same job that I need it to do. So I'm kind of curious. So I write a bit of code that does the same thing. I generate my X, that's my 0 through 13, my day identifier. I put in some 1s, that represents the constant for calculating the intercept, because here I have to specify the intercept manually. I stack those 2 columns together, pass them into the least square function, and I get out my M. And then I want to check that these things work the same and check if there's a speed difference. So I do my first bit of profiling. I use the %timeit function. Who's used %timeit inside Jupyter Notebooks? A bunch of you. All right, those of you who haven't, super easy way of using magic's % functions. We use this magic inside Jupyter Notebook, and it runs a function, a convenience function. In this case, timeit will run our function in a fixed block of time to find out how long it takes and then give us some statistics back. I run my scikit-learn version, and it takes 500 microseconds there. I run the least square version, and it takes 196. It's 2.5 times faster. So that's kind of weird. Why is it 2.5 times faster for what should be the same job? Now, I always make the assumption whenever I'm doing any client engagement, the data is trying to get me fired. I'm a consultant. My job is there to enable and accelerate something, but I work in a defensive context. This thing is trying to get me fired. It's trying to embarrass me. It's trying to make me look really, really stupid. So I'm always testing to make sure, have I made a mistake or is there a problem with the underlying system? So here we've got 2 sets of results. One works 2.5 times faster than the other. I don't know why. I haven't looked at the source code yet. We'll look at that in just a moment. I want to find out, have I got the same results? Have I just done the wrong calculation and that's why it's going faster? So I import from numpy the assert array almost equal function, and I pass in the 2 arrays of 100,000 results of M from the 2 different functions, and that passes. So I've got the same results coming back. And when it says assert array almost equal, that's by default to 7 decimal places, and you can specify the number of decimal places that you want to calculate against. So we know that we're getting exactly the right number or the right set of results coming out. So what's going on? Why is it so much slower? Would anyone like to volunteer a guess why it's slower? Go on, volunteer a guess. Somebody, go on. A limitation on scikit-learn. Oh, the implementation, absolutely, right. And that's an important point. So it feels like scikit-learn is slow, but maybe it's doing some other work. Maybe it's actually doing something in our favor. And that's absolutely the right point. So we can use the line profiler. Who's used Robert Kern's line profiler before? Right, almost everyone doesn't know about this module. It's brilliant. We get a line-by-line breakdown for any of our scientific code as to where the time is being spent. So you get to find out what's slow in like one line's call. It's brilliant. So there are 3 different interfaces. There's a magic inside Jupyter Notebooks. Here I'm using, up at the top there, the line profiler, the programmatic interface. But there are 3 different interfaces. You can use it in a notebook very easily. I tell it that I want to profile the estimator.fit function from scikit-learn, and then I call it with lp.run, so lineprofiler.run, and I give it my est, fit, x, and row.value. So I pass in 1 row from my data set and ask it to then print out the statistics for how fast every line ran and where the time was spent. We get this breakdown from the fit method, and there's a lot of lines. It's actually quite a long function. I've cut out most of it because there are 3 sections that take time: check xy, pre-processed data, and then linear algebra least square. So we've got our linalg least square function. That's exactly the same function that we were using before. That's why we get exactly the same results. It does the same job. But 65% of our time is spent in these other 2 functions. And that's because we're passing in a small amount of data, not a large amount of data, but a small amount of data many times. There's a lot of overhead in the checking. Typically, with scikit-learn, we're not passing in lots of small arrays. Typically, we pass in 1 large array. So maybe 10,000 rows of data, many columns, and then we do our linear algebra, do our least squared fit on that. Here, instead, we're just passing in 1 column of 14 items, fitting against a column of 14 items, and we're doing that 100,000 times. So the overheads that make scikit-learn safe to use, which is important, those overheads add up in this context. So that's why it's running slower. So it's not the case that scikit-learn is slow, it's the case that scikit-learn is safe. And I've certainly been fixed a number of times in my development with scikit-learn where it says, Ian, you've gone and passed in some nans in that array, or you've passed in that column, it's the wrong shape. And then, of course, there'll be some really weird debugging things that come out of that and might cost me a lot of time, but the safety checks in scikit-learn get rid of all of that and just point out that I've made a mistake and I can quickly go and fix it. So it makes my life easier, generally. If we were working online on a large data set, we trusted our data, everything was bulletproof, it was well tested, we might not want those checks, and there's no way to turn them off in scikit-learn, and so then maybe you want to go and use an alternative implementation. And that's what we're going to do here, because we trust our data. But it's worth understanding that you've got a mechanism to understand why these things are running slowly, so that you can make a reasoned judgment. Do you want to turn off those safety checks and go and do it the fast way, or do you want to keep those safety checks because things are working fast enough for you? So I super recommend the line profiler. Whenever I give a talk like this, it turns out most of the room have never come across the idea of profiling, maybe beyond the C profile module in Python, and this is a bit of a revelation. So go and try the line profiler. It makes your life better. You can profile any of your code with it, and it helps you identify not where you think the problem is, but where the truth of the matter is relative to your implementation and your data set. Because one thing I keep finding after 15 years of doing this is that my assumptions are kind of right, but they're kind of wrong too. And if I were to go and put implementation effort in fixing something that I think is wrong, probably I'm doing the wrong thing. I'm way better off measuring ahead of time and then making an evidence-based judgment about where the slow thing is that I need to fix. So now we're going to proceed with the NumPy linear algebra least squared solution, not the scikit-learn solution, because that's the faster one and we trust our data, and our data is of a homogeneous type. We know what it looks like. We're very happy with it. I just want to crank the numbers quickly and get my results. But I'm not quite sure which Pandas solution I'm going to use, so I'm going to work through a set of them and do some time measurements and then see what drops out at the end. So we start with the simplest possible solution. This This is not idiomatic Python, this is not idiomatic Pandas. So when I say idiomatic, I mean not the standard way of doing it that we'd always come across, but it's a simple way of doing it. Certainly, this is how I started using Pandas back 7, 8 years ago when my mental model was broken about what Pandas was doing. So, right, I'm just going to iterate one line at a time until I get my thing working, then I'll figure out a better way of doing it. And if you come in from other languages, iterating, having a counter, and then dereferencing on a line-by-line basis, totally sensible thing to do. And actually, I still use this method. I don't use it frequently, but when I'm debugging my code, having a loop where I can build up a partial result and I can put breakpoints in under conditionals, it's a super sensible thing to do. So I actually still use this method, even though every Stack Overflow post will tell you, don't do it this way, it's the wrong way to do it. It's a slower way to do it, it's not necessarily the wrong way to do it. So we build up range, so we're going to iterate from 0 through 99,999 over our 100,000 rows. We get a counter, and then we go into the data frame. When we say data frame, give me this row, so we have to do some mechanics getting the counter. We go into the data frame, we find the row, we make a new series, we pull it out, and then we pass it into our function. There's a whole bunch of overhead there. This solution takes 20 seconds. And because I'm defensive, you see at the end I've got an assert check there to make sure that this result is the same as the result I calculated previously. I'm always very defensive in this, and you should be defensive too. So 20 seconds, but reasonable, but this is not going to scale up. So then we look at the Pandas iterrows solution. Who's used iterrows? Okay, yeah, so this is another common way of doing it. I personally don't tend to use iterrows. I tend to use the iloc if I'm going to iterate one line at a time. Iterrows gives us an iterator. Now this becomes idiomatic Python and idiomatic Pandas. Not super efficient, but idiomatic. So it's a way that the rest of your team would understand. We just iterate over a list. We iterate over a set. We iterate over any of the iterable objects in Python. So we can iterate over the rows in a Pandas data frame. Fine. This means that we're not generating an index, which we then pass into the data frame, which then has to do a bit of calculation. Instead, it just starts yielding off rows one at a time. It's more efficient. So rather than 20 seconds, we get the same result out in 12 seconds. So it's nearly twice as fast. It's pretty cool. It's not at all as fast as we can go. It's nice and easy to write. Really, I'm guessing if I say who uses apply, we're all going to put our hands up, because apply is the very standard way. So who uses apply? Yeah, right, so most of us do. Those of you who don't, those of you who are earlier in your Pandas journey, look at apply. It's the standard way of doing it, and your code will run quite a lot quicker as a result. We get down to 7 seconds. We've got a 3 times speed up just for using the right way of applying a function to many rows of data. And this is completely idiomatic Pandas, not idiomatic Python, but idiomatic Pandas. So this is super sensible, and the nice thing is it's 3 lines of code. Your colleagues will understand it. There's no confusion. This just works. You can trust this thing's going to work entirely. So we'll use apply. It works fast enough, but it won't scale up still. Who's used apply with raw equals true before? There's got to be a couple of you. Brilliant. All right, you've all learned something new in that case. Excellent. So what's going on here? In the previous examples with Pandas apply, we're passing in a series, so one row of data, as a series object into our underlying function. That underlying function, those least square functions, take the series called row and get row.values. They pull the row.values out to get the underlying numpy array. When we call raw equals true, we don't make a series object on top, so we avoid all the overhead, the extra machinery of making that series object, because the function that's the target doesn't need it. We're not doing any time series operations there, we're not using any Pandas fancy manipulations on top. I just want the underlying numpy array. So the apply raw equals true passes in the underlying numpy array, gets rid of all that temporary object creation, so it runs faster. So that's quite nice. So super simple take-home view there. If you're just calculating on the underlying numpy array and you're doing it for a lot of rows, you can pass apply raw equals true, and your code will run many times, well, faster than the apply version and many times faster than the naive way of doing it. And this opens up some other interesting possibilities with compilation, which we'll get to in a little while. Yeah, so that where the arrow's pointing, where I've called linear algebra least square, we've got row. We're not using row.values anymore because it's not a series, it's just row, the underlying numpy array. Who's come across Swifter before? Only 3 of you? Okay. So one of the frustrations when working with Pandas is always that doesn't work multi-core. A lot of the time it's not multi-core. Some of the internal implementations are improving and we get to go multi-core, but on my laptop here I've got 4 physical cores and 4 hyperthreads, so I've got 8 overall. When I want to use those 4 cores, quite often it doesn't use 4 cores. It just uses 1 core. So I'm sitting there thinking, well, I'm running at 25% of the speed that I could be running at, and I've got to wait an hour. That's really boring. I wish this thing would go faster. So we have this library Swifter. I think it's 2 years old now. It's a really young project. It's a really good project to go and make some contributions to if you're curious. I've made a contribution to this. The author's dead keen to get contributions, so you can go and have a look for this. It sits on top of the Dask module, which I'll introduce in a moment, and then it lets your code run multi-core. And it does it, it's pretty clever, but with the cleverness, there are some heuristics. It doesn't always work. What it does is it samples your code, so it runs your function, first of all, on a snippet of data, and tries to figure out if it runs quick enough that it's worth, or slow enough that it's worth parallelizing, or quick enough that it's worth doing another execution path. It tries to make some heuristic-based judgments about whether it wants to go multi-core, or whether it wants to go single-core and applied in a different way, like with the applied raw equals true. Those overheads add up when it's doing that first testing, and its decision-making isn't perfect. So some of the time when I use it, your code runs faster. Some of the time when I've used it, your code runs slower. So the simple bit of advice is try it, use % time it, see how it runs. If it doesn't work, you've tried it, 2 lines, it costs you 5 minutes, you just stop using it. And if it does work, brilliant, it works several times faster and you get a nice speed up out of it. So here we've got down to 1.5 seconds from our 6 seconds before. So we're now running about 4 times faster. It's brilliant. So I just wrote an extra line of code. We import Swifter, and then you get Pandas dataframe.swifter.apply. So a simple interface change, it inserts itself inside your regular data frames. And then we've just given it the same least square raw, raw equals true. And then this runs on 4 cores on my laptop automatically. Everything goes faster. So when it works, great. When it doesn't work, we can just ignore it. Who's used Numba before for compilation? Okay, more hands there, okay. So Numba's great. When I first wrote about Numba in my high performance book 6 years ago, Numba was still immature. So in the current version of the book, any of you that come to the book signing and get a copy, you'll find that Numba's given a couple of pages where we say, hey, it works. You can put in like a 5, 10-line function. It probably compiles. But don't use it in anger because it's a bit immature. That has changed now entirely. Numba's pretty mature. It doesn't support classes, but for any single function or sets of single functions, particularly those that have for loops iterating around numpy arrays, Numba goes really quick. Here we go from the 5-second solution to half-a-second solution. And all we did was put @number.jit, so a decorator number.jit. We put a 1-line decorator in, and then magic 10 times speed up. Woohoo! This is a really, really nice speed up for no effort at all. You'll see on that decorator at the top, no Python equals true. So if you don't put the decorator up there with no Python equals true, if you just leave it as the default empty JIT with round brackets, then when Numba compiles your code, it will check to see if there are any sections that are pure Python, and then it won't compile those, it will leave those as pure Python, and then it will check to see the sections that are NumPy based, and it will compile them. If there's a problem in the NumPy section, it will treat it as pure Python code, so it will silently finish and run your code. You won't get a benefit of compilation, and you won't know that anything's gone wrong. So it's correct and it works, you just don't get a speed up and you wonder what's going on. If you put in no Python equals true, it will raise an error if it can't compile your code. It will say, look, it's not just pure NumPy code you've given me some other stuff that I can't compile. And then you'll know that a function like the one we're passing in here, a super simple function with some linear algebra, a couple of lines long, it will raise a problem if it can't compile. It does turn out that you have to write your code a little bit differently sometimes. I actually adapted the function that I'm using here from the first version that I had. I think there was a problem with, I'm passing in a tuple into VStack. Before I think I had passed in a list into VStack. A list is modifiable, a tuple is non-modifiable. And I think there was a problem with the compilation, so I had to change a little bit of the code on a couple of lines and then propagate that through for all the other examples. So Numba is a little bit fussy when it does its compilation, but when it works, it just works really nicely. Now, The important thing to note here is that we're passing in the least square raw version. That's because Numba will not compile any Pandas code. It has no machinery for compiling Pandas at the moment. It may have machinery for compiling Pandas later. So it can compile NumPy very happily, but no Pandas. So this is where we want to pass in that raw equals true, so we pass in the underlying NumPy array, none of the Pandas machinery on top, and then Numba just compiles quickly. You'll note also, after I've written the function, there's a single call. I've called it on one line of the data frame. That's because when I pass in the function for the first time, it's just in time compiled. That costs a couple of seconds. So the first time you run it, it costs a couple of seconds, then it goes really quick, and then your speed timings will be all off. So I call it once and just don't care about the time it takes, the couple of seconds to compile it, and then the subsequent runs down there, they run at half a second. So the first time you use Numba, just be aware that the first time you call it has to do that compilation. Everything will freeze for a second whilst that happens in the background. It will use LLVM, compile it to be CPU specific or GPU specific, and then it will run your code very fast afterwards. I super recommend trying it. Don't give it more than a page of code at a time, because it's quite hard to debug when things go weird. Try to restrict yourself to whatever bottleneck you have inside your code, so use the line profiler to understand where your bottlenecks are and compile just that bottleneck, and then after that things will go very quick. And of course you can apply the compiled function on your Pandas data frame, which is really nice. And you can package it up in other bits of the ecosystem like Dask, which we'll come to in just a moment. Who's used Dask? Who's used Dask for multi-core? And who's used Dask for doing distributed processing of large files? That's the other major use case for Dask. Okay, a couple of you. Anyone use Dask for pure Python parallelization? Okay, one. Okay, so Dask has got a bunch of uses, as you probably guessed then. So we can use Dask to enable our pure Python and our Pandas and our NumPy code to go multi-core. So I can take a Python, the equivalent of a bag. So a bag is some kind of structure, like a list or a set in pure Python, and then Dask will split that up and run it multi-core so that we can do our calculations on our long list of JSON objects across multiple cores quickly, and then it combines the result back. So it's a bit like using Apache Spark, but it does it on a single machine across one or more hard drives. And it'll do that on pure Python. We've got an array, which is like the NumPy array, so we can take terabytes worth of data stored on hard drives, and then Dask will split up our calculations onto different strided chunks of our disk-based large array, and then it will calculate in parallel and then combine the results back. Or we can pass in a Pandas object and we get a distributed data frame. And a distributed data frame, that's actually a collection of partitioned data frames. The typical example is to take, say, 10 CSV files. Each CSV goes into one of the partitions. You calculate in parallel on those different CSV files and combine the results together. So I used to describe this as a poor person's Apache Spark. That's a really unfair characterization. I use it. I'm not poor. I'm not poor in terms of lack of resources. We could spin up Spark clusters. We could hire a team to maintain the Spark cluster. But typically, for a lot of the cases that I work on, I don't have a massively distributed, resilient, high write throughput scenario to deal with. I've just got more data than I can fit into 32 gigabytes of RAM. And so when I want to use it, either I want to calculate on lots of gigabytes of data, and in which case getting it sharded up in some kind of way on a single machine on a terabyte hard drive works perfectly fine, or I've got a Pandas data frame where I'm only using one CPU to run my apply function, and I want to run it in parallel, and at which point we can ask Dask to run it in parallel. There's also a Dask ML which does scikit-learn in parallel in the background. And that will do things like your hyperparameter optimization across multiple cores. So here's what our Dask solution looks like. You'll note that we're calling ddf.apply, so our distributed data frame, and we're just passing in the least square raw, the number variant. So I've actually, in this case, used Numba to compile my function up, and then I've passed it into Dask. Dask runs it multi-core, and in this case, it runs twice as fast as it was running before. I've given it 8 partitions, so it's split my 100,000 rows into 8 equal-sized sets, and it sends those off across all of my cores, and it only runs twice as fast. And you may say, hey, Ian, that's not quite so impressive. The reason is now the overhead of passing data around and dealing with the mechanics is beginning to be a dominant factor, and the fact that we've got this compiled, just-in-time compiled Numba solution means that the calculations are running very quickly, so there's this overhead of passing data around that's slowing things. If we think about that Swifter example that we had a few slides back, where it ran 4 times faster on the non-compiled solution, Swifter sits on Dask. It makes some heuristic guesses, and then it uses those lines of Dask in the background to split the work up. So it's doing exactly what Dask does. And actually, if you use the Swifter solution with the Numba compiled variant, the one that I'm using on this slide, Swifter runs slower. Doesn't run as fast as the Dask solution, because the extra overhead when it's doing its heuristic-based judgments gets in the way, and the whole thing runs a bit slower. And that's why I broke those examples out that way. So you have to do a little bit of thinking, a little bit of manual checking as you work through and try these different solutions and think about the right way to apply them. I used Dask very happily on one of the Kaggle, the Quora question pairs competition. It's probably going back 3 or 4 years, where you get 1 million question pairs as pairs of strings. I was loading it into RAM, and then I was really frustrated that my text distance metrics as my first features for my machine learning were running so slow, and I just used those couple of lines of Dask, and then it went 4 core, went 4 times faster, and that was it. I made a coffee and I got on with my work, and that was brilliant. So this became part of my pipeline. Super rock solid, very well trusted. I know companies using it in deployed situations, so everything is good there. So let's just have a little reflection on where we got to and what the possible costs are of these different solutions, and I'll give you some advice on being a performant programmer, and we can wrap up. So what are the costs on the big version of this problem? We've got our 100,000 rows, and we've got a single time window of 14 days. If we make it 100 times bigger by just saying we want 2 years worth of data, and we're going to calculate M for each of those 2-week slices going back over 2 years, so it gets 100 times bigger. And let's say at the beginning we hadn't been that diligent, we were just cracking this out and just having a go. So we'd use the scikit-learn solution, which is 2.5 times slower than the linear algebra least square solution, and we were using the ILOC method, the one that has the most overhead, way back on the first slide. So that bigger version of the problem would take 90 minutes, an hour and a half. It's not the end of the world, but you don't want that in your interactive workflow, that's too slow. If we did a bit more work, a little bit of Googling, we found that NumPy solution, so it goes 2.5 times faster, and we use apply with raw equals true, so we're just passing around those underlying NumPy arrays and getting rid of some of the Pandas machinery, 10 minutes. So an order of magnitude speed up for a little bit of diligence. That's not bad. And it's not perhaps the case that we're doing just this single calculation to generate these M's. Maybe that's one of a class of examples that we need to calculate, and so all of these 10 minutes or 90 minutes add up into quite a big thing. So an order of magnitude speed up, not to be sneezed at, and that probably cost us 10 minutes work to get there, so that's pretty cool. If we use Numba, we go from 10 minutes to 1 minute. Way, another order of magnitude speed up. That's amazing. So a few more minutes work. With Numba, if you just try it, if you do it, and you remember to use that no Python equals true, it will give you an error if it can't compile, but if it can compile, the first time you run it, it'll have the overhead of the compiling cost, and after that, it will just go faster. So you've got 2 easy ways there of making your code an order of magnitude faster, at least relative to this data set, but you'd expect to see similar speed ups on your own work. In this case, if we add in Dask, it runs twice as fast again with that Numba solution. So we get 180 times theoretical speed up over the worst way of implementing the solution to our best way here. But then there's that important point down at the end. We have to remember not to go crazy. We don't want to go compiler happy. I've certainly gone compiler happy in the past. I've sat back there and thought, oh, I can make this thing go as fast as possible. I can cache optimize. I can check my L3 cache performance statistics down at the CPU level. I can make sure that my data is being shuffled around appropriately. I can go Fortran layout or C layout. I can get all the way down. And then some days later, I think, yeah, I was running in 1 minute before, and now it's running in a couple of seconds, and it's only cost me 3 days. I probably went a little bit too far with that. And it's very easy to get seduced into this world of thinking, hey, I've got so much power now, I'm just going to go faster and faster. But you need to make sure that your team can work at a suitable velocity as well. So you're thinking not just about your immediate needs right here, right now, but also about your team's development velocity, long-term ability to develop code that's reliable, maintainable, so that everyone can carry on being performant over time. So in this case, personally, I'd probably stop at the Numba point, because that's a one-line change and I can comment it out very easily. Or I might do the Dask solution, combining Dask and Numba. There's kind of a lot of moving parts at that point for very little additional gain, so I probably wouldn't go as far as combining the two of those. And I'd certainly be hesitant about using something like Dask with other team members who are less used to multi-core performance characteristics and who might have laptops with different numbers of CPUs. If you've got a MacBook Air, you've got 1 or 2 fast CPUs. Here I've got sort of 4 going on 8 of them. So characteristics would change quite a lot. So let's begin to wrap up and think about being highly performant. The iLock solution on that first line, iterating one line at a time, it's the wrong way to do it, but I still do it. I find it performant from a development and debugging perspective. It's not a bad thing to do, and apply is a very sensible thing that you should all be doing. You should be caching where you can. So with one of my client gigs recently, I've gone from waiting up to 30 minutes for some of my code to run to generate some of my features for investigation, using actually the Python built-in shelve module, which is a persisted dictionary on disk, to cache my data. So I cache it once, and then for the next week I just use the cache, and it has the speed of a dict lookup coming off of my SSD, so it's nearly instant, and I don't have to do any more pre-calculations. It's brilliant, it's old school, the shelve has been there since Python 2, it goes back a long time, it just works. There's also the LRU cache, the least recently used cache inside the functools module, and there's a library called joblib, which has a memory caching system, which is really quite clever. If you're interested in caching, have a look at joblib and look at the memory module in there. That's very nice. For development, I would always recommend using scikit-learn and not going around its safety checks, but maybe if you really care about performance, then going to, say, a pure numpy solution, which doesn't have the safety checks around it. Maybe that's a good idea, but you have to make that judgment for yourself. Numba and Dask, well, you need your team buy-in for that. You don't want to be confusing your more junior colleagues and colleagues coming in from other languages. Having confusion in the team, which causes people to write the wrong code so that things break, that stops the whole team, that breaks your flow. That's a really bad idea. It's probably not worth gaining seconds at the expense of that. But if you've got a highly performant team who are used to what's going on with some of these technologies, brilliant, give it a go. Always profile everything. If there's a take-home that you get from this talk, it has to be, go and measure it. Go and find out what's slow. Go and put some t equals time.time, t2 equals time.time around a couple of lines of code and print out the delta between them and just move those time statements around to see what's causing which bits of your code to go slow. Reason about why things are slow. Even better, use the line profiler or use the C profile module, but just measure why things are running slow, or where things are running slow, so you can reason about why they're running slow. Once you've got that, you can do everything else afterwards. You can make things faster, but you have to do it evidence-based. And test everything. Who uses the Bulwark module to test their Pandas data frames? Right, almost no one knows about this. It's a young module. It's not perfect. I'm trying to make some additions to it. There's a guy supporting it. It's a really nice module. It's basically providing a schema around your Pandas data frame, so you can say things like, this column should have no nands in it, and this column should be increasingly integer positive, and this data type should be a category data type for this column. It's a simple schema, but when you put that in the middle of your notebooks as you're developing your code, when things go wrong, you get the error at the point of error, not where it's propagated to something later, which causes your debug cycle to get really weird. So I recommend using or trying the Bulwark module. Okay, so I mentioned I'm doing a book signing later on, and that's, I think, 3:45, it's on the schedule. O'Reilly has kindly sent 25 copies, so there'll be a limited number to sign. I give these away for free. Normally, I just give them away for free. Today, I'm going to suggest a trade, but it's a pretty simple trade. I would like some feedback about where your high-performance problems are, because I'm interested in that, in exchange for a book. If you don't have high-performance problems, you get a book anyway, as long as you're in the queue. But I would very much like that feedback. I run some training courses. They're starting at the beginning of next year, one on successfully delivering data science projects, so thinking about how to de-risk them, things that cause them to break, where your exploratory work isn't enough, and firming it up. One on the software engineering side, so writing tests to make your team performant and refactoring code to make it clean. And I'm strongly thinking about adding a high-performance course, so for maybe March. So I'm very keen to get your feedback, and that's what I'm really hoping for from this audience, to get your feedback on where your high-performance problems are with Python so that I can think about that. Okay, final slide. So measure, don't guess. That's your one take home. Measure, don't guess. And test everything. Do not be messing around with not bothering to test to save a couple of minutes. Recently, I saved myself a couple of minutes on a client gig by not testing, and then a week later I realized the last week's worth of results were wrong. They weren't massively wrong, but they were just a little bit wrong, and I'd saved myself at least 3 minutes by not writing a test. I'm an idiot. After 19 years, I'm still an idiot. We all do this. Don't save your time, write your tests. One request I have of audiences when I speak now, I've been asking this for a couple of years, is please send me a postcard if I've taught you something. It's like a physical bit of feedback. Tell me what it is you remember that you learned. You can send it whenever, wherever around the world. I got that one from a talk that I gave at PyCon UK a couple of years ago. I got it from Texas a couple of weeks ago when the lady who watched the talk online heard my request and then sent me a postcard. So I'm very happy to receive these postcards. If I've taught you something, I would love to receive a postcard. Send me an email, I'll send you my address. I've got an email list which is up on my blog. It goes out every 2 weeks. It has jobs from the Pythonic data science community and my recommendations for videos and books that I've read and the like. That might be interesting. And then all of my past talks are listed up on my blog, ianozsvald.com. Thank you very much.